This video is going to be on special relativity, and we're going to look at how Einstein messed with space and time. Prior to this, space and time were considered fairly constant, like time ticked on at a fairly constant rate, and space, you could know the length and the width and the height of something, and that would never be messed with. You could measure it, and you could get a solid idea of what an object's length, width, or height was. And Einstein changed all of that. Alright, so we have to talk about relativity in general. And a way to think about relativity is to think about right now as you sit here watching this video, how fast are you moving? Well, if you're sitting in a chair, you're going 0 meters per second relative to your chair. The Earth is rotating, right? This was what gives us a day. It rotates, and from the center of the Earth, we're moving at about 400 meters per second because of the rotation. Now, we don't feel that because everything moves with us. The atmosphere, there's no wind, the atmosphere, it's all moving at the same rate, so we don't feel that movement, but we are. The Earth also revolves around the sun, and so relative to that, we're moving 30,000 meters per second. And then the entire Milky Way is orbiting, and we're about 2/3 of the way out of one of those arms. So, and relative to the center of our galaxy, we're moving 220,000 meters per second. And then we can take it and compare it to other galaxies and go on and on and on. So, we have to figure out relative to what. And Einstein came up with this idea that, velocities change relative to what you're looking at. The only one that doesn't is the speed of light. That one is constant. Alright, so when we look at the speed of light, and we look at figuring out the speed of light, there were two scientists who famously measured and figured out the speed of light, and that was Michelson and Morley. And back then, the idea was, if you have a wave, and light is a wave, it must wave through something. It can't wave through nothingness, or so they thought. And so all the scientists thought there was this thing called ether, that there must be just this, I don't know, not quite a liquid, but this thing that the whole universe was in, and we could just find it and measure it. And Michelson and Morley proved that ether didn't exist, and they did so in the measurement of light. They found that light does not speed up as the Earth moves directionally. You can go, as the Earth rotates and as the Earth revolves, you might think that you could move into the light, that beam that you're setting off, and by moving into it, you would speed it up, right? You would give it some additional velocity, or if you're moving away from the source, you would give it you would slow it down. They really found that it doesn't matter which direction it's going, light travels at the exact same speed. And so this is 1887. But no one really realized quite how much that kind of screwed everything else up. Just saying, okay, well, the speed of light is constant. Well, okay, what's the big deal? One thing it did was, like I said, it got rid of ether, and that really upset a lot of scientists. There was a bunch of scientists who just thought that could not happen. But it also made light constant. When you do that, you start messing with space and time. Alright, so we now have this constant speed of light, and that doesn't change regardless of the motion of the observer, whoever's looking at the light. So as we look at sort of all inertial frames, and when we mean inertial, that's a constant velocity, it's not accelerating. The laws of physics are going to stay the same. Alright, so hopefully you've had a chance to watch a few of the other videos on relativity, and you can start to get the idea that it's going to depend on your frame of reference. So this guy sitting here, here's his light source, and if he's in a stationary room, or from his point of view, even if he's in a rocket, the light going this way and the light going this way are going to hit this wall and going to hit this wall at the exact same time. But if we change our perspective, we change our frame of reference here, and we have this outside observer, what she would perceive is the light source actually hitting here first and it taking longer to hit this front. And that's the frame of reference. That depends on the observer. All right. So we know that that light couldn't be going any faster in either direction. And what happens is that the time is changed. So one person's space is another time. What we mean is that we've lost simultaneousness. So it's not simultaneously hitting those two walls for those two observers. But the speed of light has to be constant. So all that's left to change is that time is no longer constant, all right? So time becomes the variable. You guys grew up in a world where time is considered sort of variable. But back in the day, people really thought of this as a constant. It's not. The speed of light is the constant. So when we look at our equation and we have space and time, you can increase space, you can increase time. They'll all give you a constant speed of light. And when we talk about the events described by 3 spatial coordinates, what we're talking about are just the x, y, and z coordinates, or if you want, length, width, and height, plus time. So we talk about a unit that is a space-time unit. All right, so now let's just imagine that we've sort of developed a clock, let's say, a light clock, and all you have are 2 mirrors. You have one here and you have one here. And now we're just going to take a beam of light and we're just going to bounce it like a ping pong, back and forth and back and forth and back and forth and back and forth. And each one should take, an equal time interval, this and back and forth, all right? Well, let's do this again. If we have a guy sitting in a rocket, this back and forth and back and forth is going to be, a certain time interval for him. And then we look at, well, what happens for this person? This light that's going back and forth now is also moving forward at the exact same time. From her perspective, it's also, this rocket's going this way, which means the path of the light is longer. It's like this. It goes up and then bounces down. It's still just going up and down and up and down, but because this whole thing is moving, it's going up and down and up and down and so on like that. And so we think, well, to get from here to here must take a certain amount of time. It must go faster here, right? This thing has to go faster. It's a longer trip. It's got to get from here to here. Well, no, it can't go faster. It's a constant. So this distance is longer. Guess what? From her perspective, this time is longer. So we actually change the time. If you think of velocity equals distance over time, we cannot change the velocity of light. It is a constant. That means all we have left to change are the distance. We have to adjust the time to keep the velocity the same. All right, so we have what's called time dilation. And we have these Lorentz transformation equations that will sort of take one frame of reference and put it into another frame of reference. And really what I want to do is just take a look at the denominator of this sucker so you can understand it. We're not going to do math with these. I don't want you to worry about math with these. I want you to just take a look at the denominator down here and just think about it for a minute. For most of the physics we do here on Earth, this velocity compared to light is almost zero. I mean, even if it's going fast, even if it's going a couple 100 miles an hour, that is nothing compared to the speed of light. 2.99 times 10 to the 8th meters per second. This thing's going nothing compared to that in meters per second. A few meters per second or 100. There's no relationship. This ratio is very close to zero, which means we're going to take some number and divide it by 1. And you divide something by 1 and it doesn't change the number. Or you're going to divide it by essentially 0.99999999999, and it's very close to 1, and you don't have to change your frame of reference for almost anything you see here on Earth. All right, so when you do that, you get what's called a gamma factor, and that's just sort of a ratio to see like how crazy your world is. For a velocity of 0, things are totally normal from our point of view, If your velocity is like 0.6, the speed of light, you're actually going very, very fast. I mean, that's insanely fast. These are particles that go this fast, not people. Things start to get a little strange, and then as you go faster and faster and faster, as the velocity approaches the speed of light, gamma is going to approach infinity, and things are going to get very, very, very strange from our point of view. All right, so what does it do? What kind of strangeness do we see? Well, when we see time dilation, the clocks on a moving platform will appear to tick slower by that factor of a gamma. You see length contraction. Things, moving objects appear to be compressed along the direction of travel by that factor. So if a very fast moving train slips past you, you would see it compressed. What's kind of interesting is I can remember a professor telling us that he had done the calculations for the width of our body, a human body, as you drive along 280 and you're near Stanford and you go over the particle accelerator there. If there's a particle that is going, it literally goes under the freeway, 280 right there by Stanford. If that particle accelerator is active and you happen to drive over it at that moment, the particle would see you as being only 2 centimeters wide. And it's not that we appear 2 centimeters wide, it is from the particle's point of view, we literally are 2 centimeters wide. And no, that's not a good diet plan. All right, time dilation. So we can figure out time measured to the observer compared to the time of the person moving or the light or whatever's moving. All right, so here's an example. Again, we're not going to be doing the math on here. It's just an example so you get ideas. If a rocket ship were to move 0.88 c, that's 0.88 times the speed of light, the astronaut could measure his heartbeat 1 beat per second. What would we measure his heart rate to be? And that would be 1 beat every 2 seconds. So that compared to us, he would live twice as long, right? He would be younger than us by half. Another good time dilation example is a real example, a true example, is a muon, is a kind of particle, and it has a lifetime for us of 2 microseconds when it's at rest here on the surface. And yet they make it from the upper atmosphere to the Earth's surface, and they shouldn't. And that's because they move at 99% C, which means that they really live for 14.2 microseconds, which is long enough for them to make it here. Okay, length contraction, we already talked about that. You're going to see something is going to appear and truly be shorter. It's going to be condensed. So, and it'll be exactly according to the velocity again. And again, in most of our everyday life, we don't see this, so it seems very non-intuitive. Again, length contraction, so it's only contracted in the direction of the approaching, or the direction of motion, I should say. So it's not that the whole thing gets smaller, it's that it contracts lengthwise in the direction of movement. All right, so if you had an example, an astronaut builds a ship 20 meters long, and he passes you moving 0.88 c. How long do we say the ship is? And for us, that would be 10 meters. So again, half, similar to the other example we did. Why don't we see this every day? Why is it so non-intuitive for us? Again, because the velocities that we are going compared to the speed of light are tiny. So your gamma's going to be, 1.000000000000005. It's not enough to have an effect that we even need to worry about measuring. Even when we do pretty precise stuff, we usually don't take into account relativity. All right. velocity addition. So, people want to talk about, if you're going forward and the train's moving forward and you're on it and you move forward. For our point of view, we just add the two velocities. And again, most of the time, that's good enough. It's good enough, all right? But the real equation is this one. It's not that velocity 1 plus velocity 2 gives you the real velocity, is that you have to have this ratio over the speed of light. And so it's always actually slightly less. So if velocity 1 is 2 and velocity is 2 meters per second, it's not really going to be 4, it's going to be 3.99999999999. All right, so here's your velocity addition examples if you wanted to do it. You can hit pause and take a look at that. All right, again, we have the same idea of the previous ones, a spaceship moving this time at 0.5 c, fires a laser in the direction it's moving. What is the speed of the light? Okay, so you should remember this. Speed of light's constant, so it's going to work out for us that it's going to come out to c no matter what. All right, the twin trip. This is a classic paradox. It's not really a paradox at all. The idea is, two identical twins say goodbye, guy gets in a rocket ship, and now he's moving very, very, very fast, and he comes back to Earth, and he's going to be younger than the twin that stayed home, and it's going to depend, again, on how long he was gone, how fast he was going, how much younger he is. All right. What would we experience at light speed? Well, it's not relevant because we're not a photon. You can't get our mass up to the speed of light. But if you were going the speed of light, I don't think we could experience anything because I think that's a verb and there's no time when you're moving at the speed of light. Everything is instantaneous. So you could cross the whole galaxy, you could cross the universe, and from our point of view, that would be exactly an instantaneous thing. The leaving, going, getting there, all instantaneous. So I don't think you can have verbs when you do that. All right, so this is the complete equation for any object. And you can see it has the E equals mc squared plus any kinetic energy if that object is moving. And what this means is if you do the math for any little bit of mass, it contains an enormous amount of energy, like an insane amount of energy. A 1 kilogram rock, or you probably, I don't want to say how much you weigh, but we're definitely more than 1 kilogram, right? We contain some insane number of joules. It's got to be enough to light the planet for like a century or more. So why don't we ever see that conversion? Well, we do, but when we talk about converting mass into pure energy, that mass is gone. So it's not like when you light a fire and you get a little bit of energy out of it. That mass is actually conserved. We're just moving bonds around. We're moving electrons and stuff like that. When we look at E equals mc squared, we're actually going to annihilate some mass. All right, so let's think about where we see experimental confirmation of relativity. And we have particle accelerators, and all over. Europe's got them. We have them here. We have the muons. You can actually see length contraction in lunar orbits. And then when we talk about E equals mc squared, the most obvious one that comes to mind are nuclear bombs and or nuclear power plants. That is where we actually take a very small amount of mass, tiny amount of mass, and convert that to pure energy. And even from the tiniest amount of mass, you can blow up whole cities using that energy. Also the sun, and anytime we talk about fission, the sun, or fusion, the sun, or fission, or nuclear plants, both of those are nuclear things. We are actually literally converting a very small amount of mass into pure energy, and we get a huge amount of energy out of it.